So, hello everyone. In this lecture, we want to understand the behavior of a sequence as n approaches to infinity, which means as n becomes large and large. So, in summary, we want to understand the limit of the sequence n as n goes to infinity. Okay. So, it can be categorized into two types of sequences. One is convergent, another is divergent. Okay. So convergent sequence, we say that n is a convergent sequence if it has a finite limit, okay, like this, and divergent if it does not converge, okay, and it may happen that it goes to infinity, it goes to minus infinity, or it oscillates, okay. So what is a convergent sequence? A sequence is a convergent if there is a limit as n goes to infinity. In other words, if for every epsilon positive you can find a natural number capital N that depends on epsilon such that modulus of n minus L is less than epsilon for all n bigger than equal to n, okay, and this means this is true, okay. So what it is saying, suppose this is these are the elements of the sequence. This is for 1 n equal to 1 n equal to 2, say 2 a3 a4 a5 a6 like this, okay, and suppose L is the limit. So take L plus epsilon, L minus epsilon. So you see that in this, so this length is 2 epsilon, and in this neighborhood except a1 all the other elements are inside this bigger interval, okay. If you take this smaller interval, then you see that except this one, this one, this one, this one, all the other elements are inside this interval, okay. So it says that somehow eventually all the elements of the sequence are inside this interval of length 2 epsilon centered at L. So L minus epsilon to L plus epsilon in this open interval, right? Eventually, so after some n. Okay, if you can find this for every epsilon, this capital N depends on epsilon, right? Because in this case, capital N is 1 in the for the bigger net. For the smaller one, for the bigger interval, right? For the smaller interval, you can take this is a1, a2, a3, a4. So n is 5. So after 4, after n equals to 4, we have all the elements inside it. And yeah, for this one, n is 2 actually, right? Because n equal to 1 is missing. So after n equal to 1, after a1, all the other elements are inside this bigger one, right? Bigger one, okay? So then we say that this is the notation, okay? So as a remark, after some index capital N, all terms of the sequence are very close to L, right? So they are very close to L, okay? The second one, if the limit exists, then it is unique. So this is fine by the definition, the first remark. The second one is it's saying that if you have a sequence, if it has a limit, it is unique. So suppose there are two limits, okay? Suppose there are two limits, okay? Then you prove that they are same. How? So what is this? We start from mod of L1 minus L2. We prove that this is 0. This you can write like this. Just add and subtract with n. And mod of x is mod of minus x. So you can write like this, right? So since mod of x equal to mod of minus x for every x belongs to R, this is true. Second one is the triangle inequality, since this is less than or equal to mod x plus mod y for every xy in R, right? So this is less than or equal to this plus this. Now n converges to L1. So for every epsilon there exists n1 so that this is this. For every epsilon there exists so that there is this. Okay, you can do this. For every n bigger than or equal to 1, for every n bigger than or equal to n2. Now you take capital N equal to maximum of them. Then this says that this is less than for every n bigger than or equal to capital N, which is the maximum. So now come to this line. So this is less than epsilon by 2. This is also less than epsilon by 2. So use this, and this is true for every n bigger than or equal to n, because this inequality is true for every small n bigger than or equal to n. So ultimately we will get this is 0, which implies this is 0. So how did we get that this is 0 from this inequality, right? This is the fact. Let x is a non-negative real number. If it is given that x is less than epsilon for every epsilon positive, then x is 0. We'll prove this by contradiction. If x is non-zero, then since x is non-negative, it has to be strictly positive. Now I can choose epsilon equal to x by 2. So let epsilon equal to x by 2, which is strictly positive. Then given that x is less than epsilon, this implies x is less than x by 2. So which implies x is negative, which is a contradiction to the assumption that x is strictly positive. So x is identically 0. Now find the limit of the constant sequence by the definition of limit. So let epsilon is positive. Therefore mod of n minus k is mod of k minus k, which is 0, is less than epsilon. For any n belongs to n, so by definition of limit of the constant sequence is the constant itself. Okay. Find this limit by the definition of limit. So again we choose some epsilon positive. Now we know the Archimedean property, which says that for every epsilon positive you can find some capital N, such that if you have epsilon here, if you here, you can find some this, such that 1 by n is less than epsilon, right? Which I have written here. Now let n is bigger than or equal to this same capital N, then 1 by small n is less than or equal to this. Now this is less than epsilon, so this gives that 1 by n is less than epsilon, and 1 by n is nothing but an, right? In this case n is 1 by n, right? And this is true for every n bigger than or equal to capital N, implies that limit of n is 0 if n equal to 1 by n, right? So this is the limit of the sequence is 0, right? So that this limit does not exist by using the definition of limit. So observe that the elements are looks like this. So n belongs to n, right? So it starts from minus 1, then 1, then again like this. It oscillates, right? Suppose it has some finite limit for some L. Then for every epsilon positive, there is a natural number such that this will hold. That means L minus epsilon will be like this. So whatever capital N is, since this is oscillating, for n even it will be minus 1, for n odd it will be plus, it will be minus 1, right? For n even it will be plus 1, for n odd it will be minus 1. So the values will be exactly like this, right? For all n bigger than or equal to n. Okay. So if this is my interval L plus epsilon and L minus epsilon, it will contain 1, it will contain minus 1, right? For every epsilon positive, it will miss mainly some finite number of points up to an minus 1, and after an all the other elements are in this. So let's say this is like minus 1 and this is minus 1. Okay. Now L can be non-negative, L can be less than 0. If L is non-negative, let epsilon be positive such that epsilon is less than L plus 1, and this is possible. So basically if L is even 0, then epsilon will be between 0 to 1. So in this case what will we get? We get L minus epsilon is bigger than minus 1. So for this epsilon, this L minus epsilon is always bigger than minus 1, right? So it says like L minus epsilon is above minus 1. So I have chosen one epsilon which is positive, for which this interval does not contain minus 1, right? And minus 1 is outside basically, right? And there are a lot of minus 1. Minus 1 is repeating many times, right? Yes. So minus 1 again, minus 1, minus 1. So that cannot be a limit, right? Similarly, if L is strictly less than 0, let epsilon be greater than 0 be positive such that epsilon is less than 1 minus L. And this is possible because if L is negative, then minus L is positive. So 1 plus 1 minus L is also positive. So epsilon is between 0 to 1 minus L. In this case, we get that 1 or L plus epsilon is less than 1. So my L plus epsilon will be here, right? Less than 1. But again it misses many points because 1 is repeating many times, right? So in this outside this interval there are a lot of 1. There are infinite number of elements of the sequence. So again any negative number cannot be a limit, this shows, and this shows any non-negative number cannot be a limit. So basically there is no limit which belongs to the set of real numbers. So by definition of the convergence sequence, this limit does not exist. So this is not a convergence sequence. Okay, limit does not exist finitely actually. Now properties of limits. Okay, suppose we have a sequence an whose limit is a as n goes to infinity, and we have a sequence bn whose limit is b as n goes to infinity for some a b belongs to R. Then limit of this is a plus b, limit of this is a b. If bn is non-zero for all n belongs to n and capital B is non-zero, then limit of this is this, and the final one. Okay, if you multiply by a constant, with a convergent sequence, and the limit of that on new sequence is nothing but c times the limit of the sequence n. Okay, this is true for every c belongs to R. So we'll prove the first one. Let epsilon be positive by definition, and we'll prove that n plus bn minus a minus b is less than epsilon for all n bigger than or equal to some capital N that depends on epsilon, right? So we have this, which is this. Use the triangle inequality to get this. Now, before coming to this line, what we have done here, since n converges to a, for every epsilon positive, we can get some natural number n1 such that this will hold. Same for bn, because bn converges to b. So we have two natural numbers n1 and n2. So we take their maximum and define that to be capital N. So if n is bigger than or equal to capital N, that means n is bigger than or equal to n1, so we can apply this, and n is also bigger than or equal to n2, so we can apply this. So this is less than epsilon b2 plus epsilon b2, which is epsilon. So ultimately we get this for every n bigger than or equal to n. So that means that limit of this is nothing but a plus b. This proves the first part. Now the second part. Second part is about the product of limit of the product of two sequences, two convergent sequences. Again, let epsilon be positive. And now consider this, and now add and subtract abn and abn. So the first one you get an minus a times bn. For the second one you get a into bn minus b. This is less than or equal to this, plus this is less than or equal to this, right? So an minus a, bn is convergent, so bn is bounded. Okay, maybe we have not used or proved this until now, but we'll prove that every convergent sequence is bounded since n is bounded, right, due to its convergence. Okay, so we have some c which is, let's say, positive. Okay, yes, and here also we have this. Use the inequality mod of x y is less than or equal to mod of x plus mod y. This is triangle inequality, and then c is positive. This is this again, c is positive, so n converges to a, so I can write like this. Okay, so I can, in fact I can write like this is less than epsilon by 2c. Same thing I can do here. So I can get it, I may get different natural number n1 n2, so I'll take the maximum and I can apply this. Apparently I'll get epsilon. So this says that their product will converge to the product of their limits, right? The third one is about the quotient. Let epsilon be positive. Now consider this difference, which is this, which is this. Now since bn goes to b as n goes to infinity, so there exists a natural number such that for every n bigger than or equal to n1, we have this is less than mod of b minus 2. Since b is non-zero, so this is strictly positive, right? So we can choose epsilon to be this. So we have bn is bigger than or equal to mod of b minus this, which is the reverse triangle inequality, and you can use this to get this, right? So for every this we have this, and mod of bn is bigger than, so 2 by mod b, so 2 by mod b square times mod of bn minus b. Since bn converges to b as n goes to infinity, for every epsilon positive there exists a natural number n2 such that for all n bigger than or equal to n2, mod of bn minus b is less than mod of b square by 2 times epsilon. Since b is non-zero, so this is always this is always positive, this quantity, so we can have this, right? Now take capital N equal to maximum of this, which is a natural number. Then for every n bigger than or equal to this capital N, this is less than or equal to this, and we use this inequality here, so we'll get 2 by mod b square times mod of b square by 2 times epsilon. So this and this cancel, we'll get epsilon. So that gives by the definition of a limit that the limit of this is 1 by b. The third one is let epsilon be positive and c belongs to R, any real numbers. Consider this. If c is 0, then this will be 0, so we'll get the null sequence. The proof is fine, but whatever c is, we can start. There is nothing but this. Now c is always less than or equal to m for some m strictly positive that I can do, and since n converges to f, again we can write like this. Epsilon, take any epsilon positive, we can dominate this by epsilon by m for every n bigger than or equal to capital N for some n which depends on epsilon by the definition of a limit of n goes to a. So apparently we get this. So this says by the definition of a limit, the limit of n goes to infinity c n equal to c times a for every c real number. Okay. Next one is this bounded sequence. A sequence n is bounded if there exists a constant positive such that mod of n is less than or equal to m for every n belongs to n. Equivalently, it can be proved that there exists a real number small m and capital M such that n is bounded below by n, bounded above by n for every n belongs to n. So this is also an equivalent definition of boundedness. Okay. Examples: n equals to 1 by n, all is less than equal to 1, mod of n is less than equal to 1 because n is non-negative. N equal to sin n, mod of n is less than equal to 1. N is minus 1 power n, mod of n is 1. N is n by n minus 1, mod of n is less than equal to 1. So all are bounded. What is unbounded sequence? A sequence n is unbounded if n is not bounded. That means for every m positive, there is an n belongs to n such that mod of n is basically bigger than m. For example, mod of n equal to n is unbounded, n square is unbounded, square root of n is unbounded. Okay. Now we'll prove a very important result that every convergence sequence is bounded. So let n be a convergence sequence that it has a finite limit for some a belongs to R. Let epsilon equal to 1, then there is a natural number capital N such that for all n bigger than equal to n, mod of n minus a is less than 1. Let therefore mod of n is less than equal to mod of a plus 1, right? Because you use the triangle inequality, and this can be written like n minus a plus a which is less than equal to mod of a n minus a plus mod of a which is less than 1 plus mod of a, right? That's why I wrote this. So is this, right? And the triangle inequality. Now this is true for every n bigger than equal to 1. So after n or starting from n, if you go after n, all of n are bounded by mod of a plus 1 including capital N. So before there are finite number of elements, mod of a1, mod of a2, mod of a minus 1, and these are all finite numbers. So take their maximum. This is finite, so take their maximum. So for every n belongs to n, mod of n is always less than equal to maximum of this capital M and this, right? That says that n is bounded sequence. Yes, because mod of n is less than equal to this, and this is some fixed quantity, right? This is true for every n belongs to n, so n is a bounded sequence. But the converse is false. A bounded sequence may not be convergent. For example, n equals to minus 1 to the power n is bounded, but it is not convergent. That we proved earlier, right? So now the question is, when can we say that a bounded sequence is convergent? So at least every bounded sequence, any bounded sequence may not be convergent, but if we can we add some extra property to this bounded sequence property to make it convergent? We'll answer this question in the next lecture. Okay, thank you very much. So here we will stop.